You are standing on a planet that feels still. The ground beneath your feet does not drift. The sky does not stretch. Nothing about daily life suggests motion on a cosmic scale. And yet, everything you see, every galaxy beyond your own, is moving away from everything else. Not because it was pushed, not because it chose to, but because the space between them is growing. This expansion is not subtle. It has been measured, confirmed, and remeasured across generations. And for the past few decades, scientists have known something even stranger. The expansion is speeding up. That single fact forces a quiet assumption into the heart of modern cosmology. An assumption so deeply embedded that most of the universe's story depends on it. An assumption that says there exists something unseen, untouchable, that steadily overwhelms gravity on the largest scales. We call it dark energy, not because it is dark, not because it is energy in any everyday sense, but because it behaves like a pressure built into space itself, one that grows more dominant as the universe grows larger, a cosmic background influence that does not dilute, does not clump, and does not announce its presence except through what it does to everything else. This idea now underpins nearly everything we think we know about the universe's past and future, and that is where the unease begins. Before going any further, take a moment. If you're enjoying this kind of slow, careful journey through the universe, this is a good place to pause and subscribe. These stories work best when they unfold over time. Dark energy is not something you can point to in the sky. There is no image of it, no detector that catches it directly. Instead, it appears as a correction term in equations, a constant added to make the universe behave the way observations demand. In physics, constants are powerful. They are the rules that do not change. The speed of light, the charge of an electron, the strength of gravity. When a constant exists, it anchors reality. It tells you what is allowed and what is not. Dark energy, in its simplest form, is treated the same way. A fixed quantity, unchanging, always there. That assumption is what holds the universe together conceptually. With it, scientists can trace cosmic history backward to a hot, dense beginning and forward to a cold, expanding future. With it, they can model how galaxies form, how clusters evolve, and how space itself stretches over billions of years. Remove that assumption, and the equations begin to wobble. The universe does not collapse into chaos, but it becomes uncertain. This is not the first time physics has relied on a quiet assumption. In fact, it is a recurring pattern. When observations disagree with expectation, something must be added, adjusted, or reinterpreted. Sometimes that adjustment becomes a temporary patch. Sometimes it becomes a doorway to deeper understanding. The cosmological constant, the mathematical stand-in for dark energy, was introduced under similar circumstances, not as a bold prediction, but as a response to discomfort. The universe was doing something theory did not expect, and the math had to bend. That bending worked, almost too well. Once dark energy was placed into the equations, the universe behaved beautifully. Predictions aligned with observations. Large-scale structures made sense. The expansion history smoothed into a coherent narrative. The model became elegant in its completeness. And when a model works, questioning it feels unnecessary. But there is a subtle cost to success. The better a framework performs, the harder it becomes to notice what it assumes. The constant becomes invisible. The background turns into bedrock until something shifts. At the largest scales imaginable, distances, measured not in kilometers or light years, but in the age of the universe itself, dark energy dominates everything. Gravity gathers matter into galaxies and clusters, but dark energy controls the fate of space as a whole. Over time, it becomes the leading actor, quietly deciding how quickly the universe pulls itself apart. This dominance raises a simple, unsettling question. Why now? Why does dark energy matter precisely in this era of cosmic history? For billions of years, matter and radiation shaped the universe. Then, relatively recently, dark energy took over, not in the distant future, not in the deep past, but now. In cosmology, coincidences are uncomfortable. The assumption that dark energy is constant smooths over this discomfort. It says the timing is accidental, that we happen to live at a moment when its influence becomes visible, no deeper explanation required. And for a long time, that was enough. But assumptions have a shelf life. Every time astronomers look deeper into space, they are also looking further back in time. Light does not arrive instantly. It carries delays measured in millions and billions of years. Each distant galaxy is a historical record, frozen at the moment its light began the journey toward us. When scientists measure the universe at different distances, they are effectively sampling different eras. And when those samples are stitched together, they create a timeline of expansion, how fast the universe grew at each stage of its life. That timeline is where assumptions are tested. If dark energy is truly constant, the expansion history should follow a very specific curve. Deviations would not be dramatic. They would be subtle, statistical, easy to dismiss. But in a universe this large, subtlety matters. This is why the assumption that holds the universe together must be handled carefully, not because it is obviously wrong, but because it is foundational. When a foundation shifts, even slightly, the structure above it responds. For now, the assumption remains. Dark energy is treated as constant because that is the simplest explanation that fits the data. Simplicity is not laziness in science. It is discipline, yet simplicity does not guarantee truth. The universe has a long history of revealing that its deepest rules are not obvious. Time does not behave as expected. Space is not passive. Matter bends geometry. Certainty erodes under better measurement. Standing at this moment in cosmic understanding, you are not witnessing a revolution. You are witnessing something quieter, a careful tension between confidence and caution, between a model that works and questions that refuse to disappear. The assumption still holds, but it is no longer unquestioned. And when an assumption becomes visible, it becomes testable. If dark energy sounds abstract, that's because it is. Not abstract in the sense of being complicated, but abstract in the way gravity once was present everywhere, invisible anywhere. You cannot bottle it. You cannot shield against it. You cannot stand in its path. And yet, without it, the universe you observe would behave very differently. Dark energy enters the story not as an object, but as an effect. Astronomers did not stumble across it in a telescope image. Physicists did not isolate it in a laboratory. Instead, it appeared when something else refused to behave as expected. Galaxies were supposed to slow down. For decades, that assumption felt reasonable. Gravity pulls matter together. Over time, the expansion from the Big Bang should decelerate as matter tugs everything inward. Even if the universe never collapsed back on itself, its growth should at least ease. But when astronomers began measuring distant supernovae, stellar explosions so bright they briefly rival entire galaxies, they found the opposite. The farther back they looked, the faster the universe seemed to be expanding relative to earlier times. Something was pushing, not outward from a center, not as a blast or a wind, but uniformly, everywhere, embedded in space itself. The expansion of the universe was accelerating, and gravity alone could not explain it. That unexplained push is what we call dark energy. The name is misleading. It suggests a substance, or a fuel, or a hidden reservoir waiting to be tapped. In reality, dark energy is a placeholder. a label for a behavior we observe but do not yet understand. It is a description, not a mechanism. To make sense of it, you have to let go of the idea that space is empty. In everyday experience, empty space is nothing, a vacuum, an absence. But in modern physics, space has properties. It can stretch, it can curve, it can store energy, and under the right conditions, it can dominate everything else. Dark energy behaves as if space itself carries a kind of built-in pressure. As the universe expands and space becomes more abundant, this pressure does not thin out. It does not weaken. It remains constant per unit volume, or at least that is the assumption. This creates a strange feedback loop. As space expands, more space appears. And if space contains dark energy, then expansion creates more of the very thing that drives expansion. The result is acceleration. Not explosive, not sudden, but relentless. This is why dark energy only becomes important at large scales and late times. In the early universe, matter and radiation were dense, gravity dominated, structures formed, galaxies assembled. But as the universe grew larger and emptier, dark energy slowly took control. Today, it outweighs everything else. By current estimates, dark energy accounts for roughly 70% of the universe's total energy content. Matter, everything you can see, touch, and detect, makes up less than 30%. Ordinary matter, the kind that forms stars and planets, is only a small fraction of that. This means most of the universe is governed by something you cannot interact with directly. That realization changes how you think about reality. The familiar becomes secondary. The invisible sets the rules. Yet dark energy is not a force in the traditional sense. It does not pull or push objects locally. You do not feel it inside galaxies or solar systems. Gravity remains dominant there. Dark energy reveals itself only when you zoom out far enough, when individual motions blur into cosmic flow. This is why it took so long to notice. To understand dark energy, imagine dots drawn on the surface of an inflating balloon. As the balloon expands, the dots move apart. No dot is the center. None are moving through the surface. The surface itself is stretching. Now imagine that the rate of inflation increases over time. Even though nothing external is pumping air in, that accelerating stretch is the clue. But analogies break down quickly. Balloons exist in higher dimensional space. The universe does not need an outside. Its expansion is intrinsic, governed by equations that relate geometry to energy. Those equations allow dark energy to be represented in a very specific way, as a constant term that resists gravity. In technical language, it has negative pressure. That phrase sounds exotic, but its meaning is simple. Where normal matter pulls inward, dark energy pushes outward. This push does not tear objects apart. It does not overcome atomic bonds or planetary orbits. It only matters where gravity has already thinned out between clusters of galaxies. Across vast cosmic voids, at those scales, dark energy wins. And yet, despite its dominance, dark energy remains deeply unsatisfying. It feels too convenient, too clean. A constant that fits the data but explains nothing deeper. There is no agreed-upon origin for it. Some interpretations associate it with the energy of empty space, predicted by quantum physics. Others treat it as a separate component of the universe altogether. None provide a complete, testable explanation that bridges theory and observation. This gap is uncomfortable, especially because the constant version of dark energy raises profound questions. If dark energy is truly constant, why does its value have the specific strength we observe? Why is it small enough to allow galaxies to form, but large enough to dominate later? Why does it become important precisely during the era when observers like you exist? These are not philosophical curiosities. They are signals that something may be missing from the picture. In science, when a model works but feels arbitrary, it often means it is incomplete. Constants that lack explanation tend to be placeholders for deeper dynamics waiting to be uncovered. Dark energy may be one of those placeholders. For now, cosmology treats it with restraint. The constant model remains the simplest explanation that matches the data. It predicts observations with remarkable accuracy. It has survived countless tests, but survival is not the same as understanding. Every measurement of cosmic expansion is also a measurement of dark energy's behavior. Every distant galaxy, every supernova, every subtle pattern in large-scale structure adds another constraint. Over time, these constraints form a portrait not of dark energy itself, but of how it acts. And behavior is something science can interrogate. So when you hear that dark energy is mysterious, it is not because it is mystical. It is mysterious because it sits at the intersection of observation and ignorance. It explains too much with too little explanation. It works. And that, sometimes, is the most troubling part. Dark energy does not announce itself with drama. It does not demand belief. It simply shapes the universe quietly, continuously, and without regard for whether it makes intuitive sense. You live inside its influence right now. Every second, space grows a little larger, not around you, not within you, but everywhere at once, and that growth, guided by something you cannot touch or see, is the reason the universe looks the way it does today. Distance feels simple when you can walk it. A few steps, a few kilometers, a day's journey. But the moment you lift your eyes to the sky, distance stops behaving like something you can trust. Stars do not get smaller when you approach them. They do not reveal how far away they are by how bright they look. The universe offers no ruler, no grid, no markings to guide you. For most of human history, the sky was flat by necessity. The stars were points pinned to a dome, equally distant, fixed in place. That idea was not ignorance. It was practicality. Without a method to measure depth, the sky had no depth. The problem was not curiosity, it was geometry. You cannot reach a star to measure the distance it traveled. You cannot send a signal and wait for it to return. The scales are too large. So the first step toward cosmic distance did not involve speed or power. It involved perspective, parallax. It is one of the simplest ideas in science, and one of the most powerful. Hold out your thumb. Close one eye, then the other. Your thumb appears to shift against the background. That shift is not motion. It is geometry revealing distance. Ancient astronomers understood this in principle. If Earth moved, nearby stars should shift slightly against more distant ones as our viewpoint changed. If no shift was seen, either Earth was still, or the stars were unimaginably far away. For centuries, no shift appeared. That absence was decisive. It anchored the belief that Earth sat motionless at the center of everything, not because people resisted change, but because the measurements demanded it. The stars did not move. When Earth's motion was finally accepted, the implication became unavoidable. If parallax was real but invisible, then the stars were not just far, they were staggeringly distant. The first successful stellar parallax measurement did not come until the 19th century. Friedrich Bessel measured a tiny angular shift, less than a third of an arcsecond in a faint star called 61 Cygni. The result was not dramatic to the eye, it was profound to the mind. That shift meant the star was trillions of kilometers away. From that moment on, distance in the universe stopped being speculative. It became measurable. But parallax has limits. As stars get farther away, their apparent shift shrinks until it dissolves into noise. Beyond a few thousand light years, the method fails. Geometry alone cannot span the galaxy. To go further, astronomers needed something new, not a ruler, but a ladder. The cosmic distance ladder is not a single tool. It is a chain of methods, each calibrated by the one below it. Parallax measures nearby stars. Those stars calibrate brighter objects whose intrinsic brightness is known. Those brighter objects extend the scale to other galaxies. Each rung depends on the integrity of the previous one. At the heart of this ladder are standard candles, objects whose true brightness can be determined independently of their distance. If you know how bright something truly is, and how bright it appears, the difference tells you how far away it must be. One of the most important of these candles is the Cepheid variable star. Cepheids pulse rhythmically, swelling and shrinking in a steady cycle. Crucially, the period of that cycle is directly related to the star's true luminosity. Measure the rhythm, and you know the brightness. Compare it to what you see, and distance reveals itself. This relationship transformed astronomy. For the first time, galaxies could be placed in three-dimensional space. They were no longer smudges of light on a cosmic shell. They became islands, separated by vast oceans of emptiness. When Edwin Hubble used Cepheids to measure the distance to the Andromeda Nebula, the universe doubled in size overnight. Andromeda was not a cloud within our galaxy. It was a galaxy of its own, containing billions of stars. Distance did not just expand the universe, it redefined our place within it. But even Cepheids have limits. Beyond a certain range, they become too faint to observe. To reach deeper into space, astronomers turn to even brighter events, supernovae. Type Ia supernovae are catastrophic explosions triggered when a white dwarf star reaches a critical mass. The conditions of that explosion are so consistent that the resulting brightness is nearly uniform across the universe. These events briefly outshine entire galaxies. They are visible across billions of light years. By comparing nearby supernovae to distant ones, astronomers constructed a map of expansion across cosmic time. Distance was no longer just about where things were. It became a record of when they were. This is where measuring distance began to blur into measuring history, because light takes time to travel. Looking farther away means looking further back. A galaxy a billion light-years distant is seen as it was a billion years ago. Distance becomes time encoded in space. This realization changed the nature of measurement itself. Astronomers were no longer placing objects on a static map. They were assembling a timeline, a living record of the universe's evolution. But even this ladder required careful calibration. Errors at one rung could echo upward, distorting the entire structure. Precision became obsession. Cross-checks multiplied. Independent methods were developed to confirm results. Distance measurement became an exercise in humility. Every new technique revealed how easy it was to be wrong. Dust dimmed light. Stars aged. Galaxies evolved. Assumptions hid inside equations. Each correction brought clarity and new uncertainty. And yet, step by step, the universe came into focus. Today, distance is measured not just with stars and explosions, but with patterns embedded in the large-scale structure of the cosmos. Subtle imprints from the early universe act as standard rulers, stretching as space expands. They offer a way to measure distance without relying on brightness at all. The ladder has grown into a network. What began as a thumb held against the sky has become a system capable of mapping billions of years of cosmic history. But the principle remains unchanged. Distance is never measured directly. It is inferred, extracted, earned. Every number attached to the universe carries the weight of this effort. Behind each distance lies a chain of reasoning, an accumulation of trust, and a long record of corrections. When you hear that a galaxy is millions or billions of light years away, you are hearing the end of a story that began with uncertainty and patience. a story that did not assume the universe could be measured but insisted on trying anyway. And in that insistence, the immeasurable became, slowly, measurable. When Albert Einstein first turned his equations toward the universe as a whole, he encountered a problem that felt less mathematical than philosophical. Gravity, as his theory described it, was irresistible. Matter curved space, and curved space told matter how to move. Left alone, such a universe could not remain still. It would either collapse inward under its own weight or expand outward without restraint. But the universe Einstein believed he lived in was neither collapsing nor expanding. It was static, eternal, balanced, so the equations had to be persuaded to agree. To achieve that balance, Einstein introduced an additional term into his equations of general relativity, a constant, a subtle adjustment that acted as a repulsive effect, countering gravity on the largest scales. This term did not arise from observation. It was not demanded by experiment. It was inserted to preserve a worldview. This was the cosmological constant. In practical terms, it was a compromise. Gravity pulled matter together. The constant pushed space apart. When tuned just right, the two effects cancelled, and the universe stood motionless, an elegant solution to an uncomfortable implication. At the time, it made sense. General relativity was new. Observational cosmology barely existed. There was no evidence that the universe was changing. A static cosmos felt natural, even inevitable. Einstein's constant was not a mistake in method. It was a reflection of the assumptions of the era, but compromises age quickly in science. Within a decade, observations began to shift. Astronomers discovered that distant galaxies were receding from us. The universe was not static. It was expanding. Space itself was stretching, carrying galaxies along with it. Einstein reportedly abandoned the cosmological constant after this realization, calling its introduction his greatest blunder. Whether he used those exact words is debated, but the sentiment is clear. The constant had been unnecessary. The universe did not need help to move. For a time, the cosmological constant faded into obscurity. The equations worked without it. Expansion explained the observations. Gravity and initial conditions did the rest. But the story did not end there. Decades later, a new problem emerged. Astronomers measuring the expansion of the universe expected it to slow over time. Gravity should gradually pull against the initial outward motion. The universe should coast, losing speed. It didn't. Instead, observations revealed that the expansion was accelerating. Galaxies were not merely drifting apart. They were pulling away faster and faster as time went on. The cosmological constant returned. This time, it was no longer a philosophical preference. It was an observational necessity. Something in the equations had to account for acceleration. The simplest option was the same constant Einstein once introduced, now reinterpreted. What had once been a mathematical convenience became a physical placeholder. In this modern context, the cosmological constant represents the energy of empty space itself. Not emptiness as absence, but emptiness as a medium with properties, space. According to this view, carries a uniform energy density that exerts a repulsive gravitational effect. This reinterpretation was both elegant and unsettling. Elegant, because it required no new fields or forces. The equations already allowed for it. Unsettling, because the predicted value from quantum physics was catastrophically wrong. Calculations of vacuum energy overshot the observed value by an enormous margin, one of the largest mismatches between theory and observation in all of science. And yet, the constant worked with it. Cosmologists built a model that explained the large-scale structure of the universe, the cosmic microwave background, the distribution of galaxies, and the expansion history across billions of years. The model became precise. predictive, and successful. This success came at a cost. The cosmological constant has no known mechanism that fixes its value. There is no deeper explanation for why it is as small as it is, but not zero. Why it becomes dominant only in the later stages of cosmic history. Why it allows galaxies to form before tearing the universe apart. These questions remain unanswered. In science, a constant without explanation is a warning sign. It does not mean the model is wrong. It means the model is incomplete. Constants often mark the boundary between what is described and what is understood. The cosmological constant is one of those boundaries. It represents a truce between mathematics and observation, a point where theory agrees to stop asking questions for the sake of progress. That truce has held remarkably well, but it has never been entirely comfortable, because the constant does something strange. As the universe expands, matter becomes more dilute, radiation fades, gravity's grip weakens, but the energy associated with the cosmological constant does not thin out. Its influence grows relative to everything else. The more space exists, the more its effect dominates. This creates a universe where acceleration is not a temporary phase, but a long-term trend, a future where distant galaxies slip beyond visibility, where cosmic structure freezes into isolation. All of that follows from a single term in an equation, a term born from compromise. This history matters because it reveals something essential about how science progresses. The cosmological constant was not introduced because it was beautiful or inevitable. It was introduced because the universe refused to match expectation. When expectations changed, the constant was removed. When observations demanded it again, the constant returned. It has been wrong for the right reasons and right for the wrong reasons. That is not a failure. It is a reflection of honesty. Models are tools. They are built to fit reality, not to satisfy intuition. When reality changes its demands, the tools change with it. Sometimes those changes persist longer than anyone expects. Today, the cosmological constant sits at the center of our understanding of the universe. It explains the acceleration of cosmic expansion. It stabilizes our equations. It allows us to predict what we see, but it does not explain itself. And that unresolved tension, the gap between success and understanding, is where questions begin to accumulate. Not loudly, not dramatically, quietly. The cosmological constant holds the universe together mathematically, but its origin remains one of the most persistent unknowns in physics. It is a reminder that agreement between theory and observation does not always signal completion. Sometimes it signals a pause long enough for better questions to form. In the late 1990 seconds, cosmology felt stable, not complete, but coherent. The universe was expanding. That much was clear. The open question was how quickly that expansion was slowing down. Gravity, after all, is persistent. Over billions of years, it should tug against the outward motion left over from the Big Bang. Expansion would continue, but with less urgency. That was the expectation. It was reasonable, it was elegant, and it was wrong. In 1998, two independent teams of astronomers were studying distant Type Ia supernovae stellar explosions, so luminous they briefly rival entire galaxies. These events were valuable not because they were dramatic, but because they were consistent. A Type Ia supernova reaches nearly the same intrinsic brightness every time. That reliability made them cosmic mile markers, visible across enormous distances. You measure how bright one appears. You compare it to how bright it should be. The difference tells you how far away it is. Simple in principle, demanding in practice. As these teams looked deeper into space, they were also looking further back in time. Each supernova was a snapshot of the universe at a different age. Together, They formed a historical record of cosmic expansion. The goal was straightforward: measure how the expansion rate had changed over time. Confirm that it was slowing down. Instead, the data began to suggest the opposite. Distant supernovae appeared dimmer than expected, not slightly, significantly. The simplest explanation was that they were farther away than they should have been if the expansion had been decelerating, which meant the universe was expanding faster now than it used to. Acceleration. At first, this result was unsettling rather than exciting. Acceleration did not fit the narrative. It was not predicted by the dominant models. It implied that gravity was losing ground on the largest scales, that something else was at work. The teams checked everything: calibration errors, dust obscuration, evolution in supernova properties, selection bias, any effect that could make distant explosions appear dimmer without rewriting cosmology. Nothing held up. Independent analyses converged on the same conclusion. The universe was not just expanding, it was accelerating. This was not a minor correction. It was a reversal. A universe dominated by matter slows down. A universe dominated by something repulsive speeds up. The data did not leave much room for interpretation. If the measurements were right, then the majority of the universe was governed by something no one had anticipated. The announcement landed quietly at first. Cosmology is cautious by nature. Extraordinary claims demand extraordinary verification. But as more observations accumulated, resistance faded. By the early 2000s, acceleration was accepted. The universe had broken expectation. This moment reshaped cosmology almost overnight. The cosmological constant, once discarded as unnecessary, returned as the simplest explanation, rebranded, reinterpreted, no longer a philosophical adjustment, but a physical component of the universe. Dark energy moved from speculation to necessity. What made this discovery especially unsettling was not just that it contradicted prediction, it was that it contradicted intuition. Gravity feels fundamental. It dominates everyday experience. It sculpts stars, planets, and galaxies. The idea that something else could overpower it on the largest scales felt almost disrespectful to everything physics had taught before. Yet the data was unambiguous. The expansion of the universe was speeding up. This realization forced a reordering of cosmic priorities. Matter, once assumed to govern the universe's fate, was demoted. Dark energy, whatever it was, took center stage. The implications were immediate and profound. If acceleration continued indefinitely, distant galaxies would eventually recede beyond the observable horizon. Light emitted in the future would never reach us. The universe would become darker, emptier, more isolated over time. This was not speculation. It followed directly from the measurements. For the first time, cosmology confronted a future defined not by collapse or balance, but by separation. The discovery also revealed something deeper about how science progresses. No new telescope had been built to find dark energy. No experiment had been designed specifically to detect acceleration. The tools already existed. What changed was how carefully they were used, and how far they were pushed. Progress came not from ambition, but from persistence. Two teams, working independently, arrived at the same uncomfortable conclusion. That convergence mattered. It transformed surprise into confidence. In 2011, the leaders of those teams were awarded the Nobel Prize in Physics. The citation was brief. The impact was not. Acceleration was now a fact of the universe, but facts have consequences. Once acceleration was accepted, cosmologists had to confront questions that had previously been academic. What is the universe made of? Why does dark energy dominate now? Is its strength fixed? Or does it change over time? These were not idle curiosities. They were direct consequences of a measurement. The year 1998 did not deliver answers. It delivered responsibility. From that point forward, every model of the universe had to account for acceleration. Every theory of cosmic evolution had to accommodate dark energy in some form, and every assumption became suspect. What made the moment especially powerful was how quietly it unfolded. There was no single image, no dramatic announcement, just a gradual realization that the universe was behaving in a way no one had planned for. Acceleration did not shout. It revealed itself through careful comparison, through faint points of light at the edge of visibility. That is often how the universe changes our understanding. Not through spectacle, but through persistence. By the end of the 1,990 seconds, the universe was no longer a story of gradual slowing. It was a story of unexpected dominance, of a component that had gone unnoticed for billions of years, only to assert itself decisively. From that moment on, cosmology entered a new phase, one defined not by what we could see, but by what we could infer, by effects without causes, by a force we could not touch, yet could no longer ignore. The universe did not ask permission to change its story. It simply revealed that the story we were telling was incomplete. There was a time when astronomy meant silence. One observer, one telescope, a notebook filled with careful sketches and handwritten numbers. The sky was small enough to fit inside a human routine, and discovery felt personal, almost intimate. That era did not end because curiosity faded. It ended because the universe proved too large. As telescopes grew more powerful, the sky stopped behaving like a collection of objects and started behaving like a data set. Stars multiplied into millions. Galaxies blurred into catalogs. Patterns emerged only when individual details were set aside. To understand the universe at scale, astronomy had to change its character. It had to industrialize. Industrial astronomy does not begin with wonder. It begins with logistics. How do you observe millions of objects efficiently? How do you collect light from different directions without moving a telescope endlessly across the sky? How do you transform photons into numbers and numbers into meaning? These questions reshaped the field. Instead of pointing a telescope at one object for hours, astronomers began surveying entire swaths of sky systematically. Instead of measuring a few stars with exquisite care, they measured millions with consistent precision. Discovery shifted from the eyepiece to the pipeline. The night sky became a production line. At first, this felt like a loss. The romance of stargazing seemed incompatible with automation. Computers replaced intuition. Algorithms replaced sketches. The sky no longer belonged to an individual observer. It belonged to collaborations spanning continents. But this transformation was not optional. It was demanded by scale. Dark energy could not be understood by studying a handful of galaxies. Its effects are statistical, subtle, spread across billions of light years. To detect it, astronomers needed patterns, not anecdotes, trends, not exceptions. That meant data, enormous amounts of it. Industrial astronomy treats the universe as something to be sampled repeatedly, uniformly, and without bias. Telescopes sweep the sky according to predetermined plans. Every object is observed the same way, processed through the same software, measured by the same standards. This consistency is not cold. It is essential. When you are searching for a signal that may change the fate of the universe, you cannot afford personality in the data. You need reliability, repeatability, systems that behave the same at midnight as they do at dawn. This is where astronomy began to resemble other large-scale sciences. Particle physics, climate modeling, genomics, fields where individual measurements matter less than the structure that emerges from many of them. The universe became something you analyze rather than gaze at. Light enters a telescope and is immediately transformed, split into spectra, converted into digital signals, stored in databases that grow night after night. The raw sky disappears almost instantly, replaced by columns of numbers representing wavelength, intensity, position, and uncertainty. Those numbers are not beautiful, they are not poetic, but they are honest. Inside them are the fingerprints of cosmic history. Redshifts encode expansion, clustering encodes gravity, voids encode absence. When processed together, these features reveal how matter has moved and how space has stretched over billions of years. But this power comes with a cost. Industrial astronomy demands trust in calibration, in software, in statistical methods. A single error can propagate through millions of measurements. A subtle bias can masquerade as a discovery. The human eye, once a filter for nonsense, is no longer in the loop. So new disciplines emerged alongside the data. Validation teams, blind analyses, simulated universes used to test pipelines before real observations are ever interpreted. Astronomy learned to doubt itself systematically. This self-doubt is not weakness, it is survival. Because when your conclusions depend on spreadsheets rather than sketches, confidence must be earned differently. Not through authority, but through redundancy, independent checks, cross-comparisons, data released publicly so others can try to break your results. The modern astronomer spends as much time debugging code as observing the sky. This shift also changed the tempo of discovery. There are fewer sudden revelations, fewer single-night breakthroughs. Instead, there are releases, data drops, papers that summarize years of work in cautious language. Progress became incremental, yet the scale of that progress is unmatched. Industrial surveys can reconstruct the universe in 3 dimensions, not just where galaxies are, but how they are arranged across time. Filaments, walls, voids, structures so large they were unimaginable when astronomy relied on individual observations. These structures are not decorative, they are diagnostic. Their shapes and distributions respond to the physics that governs expansion, to dark energy, to gravity, to the contents of the universe itself. Industrial astronomy turns cosmic structure into evidence. This is why the era of spreadsheets matters so deeply to the story of dark energy. Acceleration does not announce itself locally. You cannot feel it. You cannot watch it happen in real time. Its signature is statistical, spread thinly across billions of light years. Only a survey wide enough and uniform enough can reveal it. That requirement reshaped the culture of astronomy. Collaboration replaced solitude. Data releases replaced private notebooks. Teams became larger, more diverse, more specialized. Some astronomers never touch a telescope. Others never write code. Discovery became collective. This raised a quiet philosophical question. If no single person sees the universe directly anymore, who is doing the seeing? The answer is uncomfortable but accurate. The seeing is done by systems, by instruments designed to remove human preference, by algorithms trained to ignore what feels important and attend to what is measurable. Human judgment still matters, but it appears later, during interpretation. This separation between observation and understanding is new. It introduces distance not just between Earth and galaxies, but between the observer and the sky itself. Yet it also unlocks something unprecedented. For the first time, humanity can observe the universe not as a collection of remarkable objects, but as a coherent whole, a system governed by rules that apply everywhere at once. Industrial astronomy is not about losing wonder. It is about changing where wonder lives. It no longer lives in the act of looking up. It lives in the realization that a spreadsheet can contain the echo of the Big Bang, that a plot of points can encode billions of years of expansion, that the fate of the universe can be inferred from patterns too subtle for the eye. This transformation did not make astronomy less human. It made it more ambitious, because only by stepping back, by letting machines collect the light and mathematics extract the meaning, could humans hope to confront questions as large as dark energy? The sky did not become smaller when it entered a spreadsheet. It became legible. DESI was not built to look at the universe. It was built to interrogate it. From a distance, the Mayol telescope in Arizona looks unremarkable. A 4-meter mirror. A familiar dome. Nothing about its silhouette suggests it is part of one of the most ambitious cosmological projects ever attempted. The transformation happens inside, where light stops being scenery and becomes evidence. DESI, the dark energy spectroscopic instrument, represents a shift in how humanity studies the cosmos, not by gazing deeper at individual objects, but by sampling the universe systematically, repeatedly, and at scale. Its goal is not beauty. Its goal is structure. At the heart of DESI is a simple question made brutally difficult by size. How has the universe expanded over time? To answer it, DESI does not watch expansion happen. That would require waiting billions of years. Instead, it reconstructs expansion by reading the past. Every photon it collects has traveled across cosmic time, carrying information about where it came from and when. DESI's task is to collect those photons by the millions. Mounted at the prime focus of the telescope is a circular focal plane filled with thousands of robotic positioners. Each one holds a fiber optic cable thinner than a pencil lead. Before every exposure, these robots move in perfect coordination, swiveling and extending to align their fibers with pre-selected galaxies and quasars, 5,000 targets at once. When the telescope opens, light from each target flows down its assigned fiber, traveling tens of meters to a bank of spectrographs. There, the light is split into its component colors, stretched into spectra that encode distance, composition, and motion. This happens over and over again. Night after night, season after season, DESI does not choose targets based on how interesting they look. It follows a plan, a survey strategy designed to cover as much of the sky as possible with minimal bias. Uniformity matters more than individuality. Consistency matters more than drama. This is what allows DESI to do something unprecedented. By measuring the spectra of tens of millions of galaxies and quasars, DESI builds a three-dimensional map of the universe, not just where objects are on the sky, but how far away they are translated into distance using redshift, the stretching of light caused by cosmic expansion. Each redshift is a timestamp. Nearby galaxies represent the recent universe. Distant quasars reveal conditions billions of years ago. Together, they form a layered history spanning roughly 11 billion years, most of the universe's life. This is the scale DESI operates on. Mapping the universe at this level is not about precision in any single measurement. Individual distances have uncertainty. Spectra contain noise. But when millions of measurements are combined, patterns emerge that are more reliable than any single data point. DESI is designed to detect those patterns. One of the most important is the large-scale clustering of galaxies. Galaxies are not scattered randomly. They trace a cosmic web shaped by gravity and expansion. Filaments connect clusters. Voids open between them. This structure carries the imprint of conditions from the early universe. DESI measures how that structure changes with distance and therefore with time. If the universe expanded at a steady rate, those patterns would stretch in a predictable way. If expansion accelerated differently at different epochs, the stretching would vary subtly. DESI's sensitivity lies in detecting those subtle differences. This is not intuitive science. It is forensic science. The instrument does not test dark energy directly. It tests geometry. It tests how distances scale with redshift. It tests whether the universe's expansion history follows the curve predicted by a constant dark energy, or whether it deviates. Every deviation matters. To make this possible, DESI relies on extreme control. Fibers must be positioned with micrometer accuracy. Spectrographs must remain stable over years. Calibration must be relentless. Atmospheric effects, instrumental drift, and observational bias must be tracked and corrected continuously. This level of discipline is not glamorous, but it is essential because the signal DESI seeks is not large. It is not obvious. It hides inside the noise of cosmic variance and observational uncertainty. Extracting it requires both scale and restraint. DESI embodies the industrial approach to astronomy, taken to its logical extreme. The sky is pre-divided into tiles. Targets are assigned algorithmically. Observations are automated. Data flows into pipelines that reduce, classify, and validate measurements before human interpretation begins. Astronomers do not ask whether a galaxy looks strange. They ask whether the dataset behaves as expected. This changes the relationship between human and universe. No one person understands DESI in its entirety. Engineers design hardware. Astronomers define survey strategies. Statisticians model uncertainty. Software teams maintain pipelines. Simulations teams generate artificial universes to test assumptions. Discovery becomes collective. Yet despite this complexity, DESI's ambition remains focused. It is not trying to explain dark energy outright. It is trying to constrain it, to corner it behaviorally, to say what it can and cannot be. By mapping 11 billion years of expansion, DESI provides a timeline, and timelines expose change. If dark energy has always behaved the same way, DESI should confirm it with unprecedented precision. If it has evolved even slightly, those changes should leave fingerprints in the data. This is why DESI matters. It is not because it promises answers. It is because it limits excuses. After DESI, uncertainty will remain, but it will be narrower. Possibilities will be fewer. The universe will have been forced to reveal more of its history. DESI does not rush this process. It accumulates evidence patiently. Each observing night adds a small piece to a much larger picture. Progress is measured not in discoveries, but in coverage. And that patience is deliberate. The universe is not fragile. It does not need to be observed quickly. It needs to be observed carefully. DESI is built around that philosophy. A machine designed not for spectacle, but for endurance. Not for singular insight, but for statistical truth. It stands as a reminder that some of the most profound questions in science are answered not by looking harder, but by looking longer and by trusting the quiet accumulation of data across time. 11 billion years cannot be seen, but they can be mapped. Light does not arrive unchanged. By the time it reaches you, it has been stretched, thinned, and reshaped by the journey. That transformation is not damage. It is information. In everyday life, color feels decorative. In cosmology, it is diagnostic. When light travels through an expanding universe, its wavelength is stretched along with space itself. Blue light shifts toward red. Red light shifts beyond what the eye can see. This stretching is called redshift, and it is one of the most quietly powerful tools ever developed in astronomy. Redshift is not a measure of speed in the usual sense. It does not tell you how fast an object is moving through space. It tells you how much space has expanded while the light was in transit. It encodes history rather than motion. This distinction matters. If galaxies were simply flying outward from a central explosion, redshift would be an ordinary Doppler effect. But the universe has no center. Expansion happens everywhere at once. Galaxies are not racing through space. They are being carried apart as space itself stretches. Redshift is the imprint of that stretching. When astronomers measure a galaxy's spectrum, they are not just identifying its chemical makeup. They are measuring how much the universe has expanded since the light left that galaxy. A small redshift means the light began its journey recently. A large redshift means it began billions of years ago. Distance and time collapse into a single number. This is why redshift functions as a cosmic ruler, not a ruler laid out in space, but one extended through time. Each increment of redshift corresponds to a different era in the universe's life, but the ruler is not marked in centimeters. It is marked in probabilities, to turn redshift into distance. Cosmologists rely on a model of how the universe expands. They assume relationships between redshift, scale, and time that follow from general relativity and the contents of the universe. Matter slows expansion. Dark energy accelerates it. Radiation mattered early on. Each component leaves a trace. This is where redshift becomes more than a measurement. It becomes a test. If the assumed expansion model is correct, then distances inferred from redshift should align with distances inferred from other methods. If they do not, something in the model is wrong. Redshift does not argue. It reports. This reporting allows astronomers to convert light into a timeline. Nearby galaxies populate the recent universe. More distant galaxies fill in earlier chapters. Quasars bright. Ancient beacons, powered by supermassive black holes, extend the record deeper still. Together, these objects create a layered map of cosmic history, not a photograph, but a cross-section through time. Each layer reflects a different balance between gravity and expansion. In the early universe, matter dominated. Structures grew rapidly. In later eras, expansion gained influence. Growth slowed. Patterns stretched. Redshift reveals where those transitions occurred. But redshift alone is not enough. It must be paired with structure. Galaxies do not just recede, they cluster. Their distribution carries the memory of sound waves that rippled through the hot plasma of the early universe. Subtle density variations frozen into place when the universe cooled enough for atoms to form. These ripples set a preferred scale, a standard ruler imprinted across the cosmos. As the universe expands, that ruler stretches, but its relative size remains known. By measuring how that scale appears at different redshifts, astronomers can reconstruct the expansion history with remarkable precision. This is how light becomes time, not metaphorically, but operationally. Every spectrum collected by a survey like DESI contains a timestamp, combined with millions of others. Those timestamps trace how space itself has evolved, where acceleration strengthened, where it weakened, where assumptions hold and where they strain. The beauty of this method lies in its indirectness. No one watches expansion happen. No one observes space stretching in real time. Instead, cosmology compares moments separated by billions of years and infers the rules that connect them. It is patient science. But patience does not eliminate uncertainty. Redshift measurements are precise, but interpretation depends on calibration, on knowing how galaxies evolve, on understanding how observational selection shapes what is seen and what is missed. Dust, star formation, and intrinsic differences all complicate the picture. This is why modern cosmology does not rely on redshift alone. It cross-checks. It compares rulers and candles. It tests consistency across independent probes. Agreement strengthens confidence. Tension signals opportunity or error. Redshift sits at the center of that process because it is universal. Every distant object carries it. Every photon remembers it. Even the cosmic microwave background, the faint afterglow of the early universe, has its own redshift. Its light has been stretched for nearly the entire age of the cosmos, cooling from a blistering plasma to a whisper of radiation barely above absolute zero. That extreme redshift anchors the far end of the timeline. Galaxies and quasars fill in the middle. Nearby, objects define the present. From these pieces, a continuous story emerges, one that does not rely on narrative, but on consistency. Redshift transforms astronomy from a catalogue of objects into a chronology. It allows cosmologists to ask not just where things are, but when the universe behaved in certain ways, when expansion slowed, when it sped up, when gravity dominated, when something else took control. This transformation carries philosophical weight. It means the universe is not only observable, but reconstructible. Its past is written into its present state, not as memory, but as geometry. The stretching of light preserves the record of stretching space. Every measurement adds another constraint, another check on the assumptions that underpin the model, another opportunity for surprise. Redshift does not promise clarity. It promises accountability. If dark energy has behaved differently over time, redshift will reflect that behavior indirectly, not through sudden jumps or obvious signals, but through small mismatches accumulated across billions of years. That is why cosmology advances slowly. The ruler is long, the markings are subtle, the stakes are high. Turning light into time is not a trick. It is a discipline, one that requires restraint, repetition, and skepticism. One that accepts uncertainty as a feature, not a flaw. Because when you read the universe this way, you are not asking it to perform, you are asking it to remember. And light, stretched across the ages, remembers remarkably well. Hints are the most dangerous things in science. They are not loud enough to demand belief, and not weak enough to ignore. They sit in a narrow space between confidence and doubt, forcing attention without offering closure. When a hint appears in cosmology, especially one tied to dark energy, it does not announce a discovery. It changes the conversation. For decades, dark energy has been treated as constant, fixed in strength, unchanging in time. That assumption is not arbitrary. It is the simplest explanation that fits the data. Simplicity, in science, is not aesthetic preference. It is restraint. But restraint does not prevent curiosity. As datasets grew larger and measurements more precise, cosmologists began asking a careful question. Does dark energy behave exactly the same way across the entire history of the universe? Or are we only seeing an average? Answering that question does not require speculation. It requires comparison. When surveys like DESI assemble maps that span most of cosmic time, they allow the expansion history to be examined in slices, not just then and now, but many intermediate moments. Each slice carries uncertainty. Each is noisy, but together they form a pattern, and patterns are where hints live. What began to emerge was not a contradiction, but a tension. When dark energy was modeled as perfectly constant, some measurements fit beautifully, others fit less comfortably. The differences were small, well within the bounds of statistical fluctuation, but they were persistent. This persistence mattered. If dark energy were evolving, changing subtly in strength over time, it would not announce itself dramatically. The universe would still expand. Acceleration would still occur. The difference would appear as a gentle bending of the expansion curve, a deviation from the expected shape. That is exactly the kind of deviation large surveys are designed to notice. The word evolving carries emotional weight. It suggests activity, change, mechanism. But in this context, it does not mean dark energy is alive or unstable. It means only that its influence may not be described by a single number valid for all time. This distinction is crucial. An evolving dark energy does not overthrow cosmology. It refines it. It replaces a constant with a function, a fixed rule with a trend. From a distance, the universe would look almost the same. From within the equations, everything would shift. Cosmologists express this possibility cautiously, often using a parameter that describes how dark energy's pressure relates to its density. If that parameter equals a specific value, dark energy behaves as a constant. If it deviates even slightly, it suggests evolution. Measurements of this parameter across different epochs began to cluster around values that were close to, but not exactly, constant. The deviations were small, marginal, easy to dismiss individually, but science does not dismiss patterns lightly. The strength of the hint was not in any single dataset. It was in the way multiple datasets leaned in the same direction when combined. Different methods, different assumptions, similar tension. This convergence did not constitute proof, but it was enough to provoke restraint rather than dismissal. At this point, it is important to be precise about what the hint is not. It is not evidence that dark energy definitely changes. It is not a claim that the standard model is broken. It is not a declaration of new physics. It is a question mark placed carefully at the edge of confidence. In cosmology, that placement matters, because dark energy dominates the universe today. Even small changes in its behavior can have large cumulative effects. A slight difference early on compounds over billions of years. The future trajectory of the universe depends sensitively on these details. This sensitivity is what makes the hint consequential. If dark energy were stronger in the past and weaker now, the expansion history would curve one way. If it were weaker in the past and stronger now, it would curve another. Each scenario leads to a different long-term fate, but none of those futures announce themselves clearly in the present. What cosmologists see instead is a delicate imbalance, a model that fits exceptionally well but not perfectly, a framework that succeeds everywhere but leaves small residues. These residues are not failures, they are invitations. Historically, this is how physics progresses. Newton's laws worked almost everywhere, until small discrepancies in planetary motion pointed toward relativity. Classical physics explained heat, until anomalies forced the invention of quantum mechanics. In each case, the hint came first, but hints also disappear. Statistical fluctuations smooth out. Systematic errors are uncovered. Improved calibration erases tension. Many promising deviations dissolve under scrutiny. This is why cosmologists speak carefully. When surveys suggest evolving dark energy, they do so with humility. They acknowledge uncertainty. They emphasize that the simplest explanation still works. They resist narrative temptation. This restraint is intentional, because the cost of overinterpretation is trust. The goal is not to declare a revolution, but to understand whether the assumption of constancy remains justified as data improves. If the hint strengthens, the conversation will change again. If it fades, the model will stand reinforced. Either outcome is valuable. What matters is that the assumption is now visible. For years, dark energy's constancy was treated as background, something to build on, not examine. The emergence of a hint, however tentative, forces that assumption into the foreground. Once foregrounded, it must be tested. This testing does not happen quickly. It requires independent surveys, different techniques, cross-checks that attack the problem from multiple directions. Patience measured in years. DESI's role in this process is not to settle the question, but to constrain it, to reduce the space in which uncertainty can hide, to say, with increasing confidence, what dark energy cannot be. In doing so, it reshapes how cosmologists think about the problem. Instead of asking, "Is dark energy constant?" they begin asking, "How constant must it be?" Instead of assuming immutability, they quantify tolerance. This shift in framing is subtle but profound. It reflects a maturation of the field, a willingness to interrogate even its most successful assumptions, a recognition that agreement with data does not equal finality. The hint did not overthrow cosmology, it made it more honest. And in a universe where the dominant force cannot be seen or touched, honesty is the only reliable guide. Whether dark energy evolves or not, The fact that the question can now be asked with data rather than philosophy marks a turning point. The conversation has changed, quietly, carefully, and once a question is asked at this scale, it does not go away. In everyday life, evidence feels decisive. You see something happen. You believe it. The connection between observation and conclusion feels immediate, almost instinctive. In cosmology, that instinct is dangerous. The universe is too large, too distant, and too slow to reward intuition. What looks convincing at first glance often dissolves under closer inspection. What appears as a signal may be a shadow cast by uncertainty. This is why evidence is not proof. When cosmologists talk about dark energy, they rarely speak in absolutes. They speak in likelihoods, confidence intervals, probability distributions. These are not evasions. They are acknowledgements of scale. When your experiment spans billions of light years and billions of years, certainty must be earned slowly. Statistics is the language that makes this possible. Every measurement comes with noise. Photons arrive irregularly. Instruments drift. Atmospheres interfere. Galaxies evolve. None of these effects can be eliminated completely. They can only be modeled, corrected, and constrained. Uncertainty is not a flaw in the process. It is the process. When a survey reports a hint of evolving dark energy, what it is really reporting is a statistical preference, a slight lean in the data toward one explanation over another. The lean may be small, it may disappear with more data, or it may strengthen. The number that often accompanies such claims, the number of standard deviations from expectation, carries more weight than it seems. A 2 sigma result sounds impressive, but it is fragile. It can arise by chance. A 3 sigma result is suggestive, but still provisional. In cosmology, 5 sigma is the traditional threshold for declaring something real. Dark energy hints do not live at that threshold, and that is precisely why they are treated carefully. Cosmology is not a field that can rerun experiments at will. There is only one universe. You cannot reset initial conditions or observe alternate outcomes. Instead, you observe different regions, different epochs, and different traces, and you hope the patterns align. This limitation forces a culture of skepticism. When data suggests something unexpected, the first question is not, "What does this mean?" but "How could this be wrong?" Systematic errors are hunted relentlessly. Calibration procedures are re-examined. Analysis pipelines are stress-tested using simulated universes where the correct answer is known in advance. If an apparent signal survives these tests, it earns attention, not acceptance. Attention. One of the most subtle dangers in statistical science is confirmation bias. When a result aligns with curiosity or desire, it can be unconsciously favored. Modern cosmology works hard to suppress this tendency. Blind analyses are common. Parameters of interest are hidden until methods are finalized. Decisions are made without knowing which outcome they support. This discipline is not bureaucratic. It is protective because the cost of false certainty is high. In the case of dark energy, the stakes are existential. A changing dark energy would reshape predictions about the universe's future. It would suggest missing physics at a fundamental level. It would alter how gravity behaves on the largest scales. Such claims demand restraint. Uncertainty also arises from the universe itself. Cosmic variance. The fact that we observe only one realization of the cosmos places a fundamental limit on precision, no matter how good instruments become. Some questions will always be constrained by the size of the observable universe. This means doubt is not just methodological, it is structural. Cosmologists live with this reality. They learn to interpret results not as answers, but as constraints. Each measurement narrows a range. Each survey trims uncertainty. Progress is measured in reduction, not resolution. This is why multiple independent probes matter so much. Supernovae measure brightness. Galaxy clustering measures geometry. The cosmic microwave background measures early conditions. Weak gravitational lensing traces mass directly. Each method has different vulnerabilities. Agreement between them builds confidence. Disagreement exposes either new physics or hidden error. When hints of evolving dark energy appear, cosmologists ask whether the tension is coherent across probes or confined to one method. A real effect should leave fingerprints everywhere. A systematic error usually does not, so far. The picture is mixed. Some datasets lean toward change. Others remain consistent with constancy. Combined analyses produce mild tension, not decisive conflict. The universe is not shouting, it is murmuring. This murmur is scientifically valuable. It keeps the field honest. It prevents complacency. It forces improvements in observation and analysis. It motivates new surveys and refined techniques. Doubt, in this context, is productive. It also reshapes how cosmologists communicate. Claims are framed conditionally. Language becomes careful. Words like suggest, indicate, and hint are used deliberately. This is not weakness. It is respect for the data. Public perception often struggles with this nuance. A headline demands certainty. Science offers probability. The gap between the two can feel unsatisfying. But cosmology cannot afford to simplify. The universe does not respond to confidence. It responds to accuracy. This is why evidence is treated as provisional, even when it accumulates. Each new dataset is not a verdict, but a cross-examination. Each improvement tightens the constraints, but rarely closes the case. In this environment, doubt is not the opposite of knowledge. It is its companion. Doubt reminds cosmologists that models are tools, not truths. That agreement with data today does not guarantee relevance tomorrow. That nature is under no obligation to conform to human expectations. The story of dark energy is shaped as much by what is unknown as by what is measured. The unknown is not a failure to be corrected. It is the boundary that defines the problem. When evidence falls short of proof, the responsible response is patience, not paralysis, continued observation, continued refinement, continued skepticism applied evenly to new ideas and old assumptions alike. This is the discipline that allows cosmology to progress without collapsing under its own ambition. The hints may strengthen, they may fade. Either outcome deepens understanding. What matters is not whether certainty is achieved quickly, but whether the path toward it remains honest. In a universe governed by forces we cannot touch and energies we cannot see, doubt is not a weakness, it is a necessity. The future of the universe is not written in stars, it is written in tendencies. For most of human history, the idea of a cosmic future barely existed. The universe was assumed to be eternal and unchanging, a backdrop rather than a story. Time belonged to planets and people, not to space itself. But once expansion was discovered, the universe acquired a trajectory, and once acceleration was confirmed, that trajectory became uncertain in a new way. Dark energy does not just explain what the universe is doing now. It determines what the universe becomes. If dark energy is constant, the long-term future is mathematically straightforward. Expansion accelerates forever. Galaxies drift farther apart. Eventually, distant galaxies slip beyond the observable horizon. Light emitted in the future never reaches us. The night sky grows emptier with time. Stars exhaust their fuel. New star formation slows. The universe cools and thins, settling into a quiet, dilute state, sometimes called heat death. Not dramatic, not explosive, just gradual isolation. That future follows directly from a single assumption. But if dark energy changes even slightly, the future bends. A weakening dark energy would slow acceleration. Expansion would continue, but its grip would loosen. Structures could persist longer. Cosmic isolation would arrive more slowly. The universe would age differently. A strengthening dark energy would do the opposite. Acceleration would intensify. Expansion would overwhelm gravity more aggressively. Galaxies would separate faster. Horizons would shrink. Isolation would accelerate. In extreme cases, expansion could become violent. Some theoretical models predict a scenario known as a Big Rip, where dark energy grows so strong that it eventually overcomes all binding forces. Galaxies, stars, planets, even atoms would be pulled apart as space expands faster and faster. This outcome is speculative and constrained by observations, but it illustrates the sensitivity of cosmic fate to dark energy's behavior. The universe does not need a large change to produce a large effect. This sensitivity arises because dark energy dominates at late times. When matter was dense, small differences were drowned out. Today, with matter diluted across expanding space, dark energy's influence compounds. Each moment of acceleration feeds the next. The fate of the universe is therefore not determined by its beginning alone. It is shaped by how its dominant component behaves over time. This realization shifts how cosmologists think about destiny. Instead of asking whether the universe will expand forever or collapse, they ask how expansion evolves, whether it speeds up, slows down, or changes character entirely. Fate becomes conditional. This conditionality is unsettling. It means the universe's future is not locked in by initial conditions. It depends on properties that may not be fixed, on parameters that may drift, on assumptions that must be tested rather than trusted. Dark energy turns cosmology into a study of long-term consequences. If it evolves gently, the universe may approach a quiet asymptote, expanding, cooling, but never tearing itself apart. If it evolves dramatically, the story could end in fragmentation. If it fades, gravity could reassert itself over unimaginable timescales. Each possibility carries a different meaning for existence. In an eternally accelerating universe, contact between distant regions becomes impossible. Communication ends. Each galaxy becomes its own island. Knowledge freezes locally, unable to propagate across an ever-expanding gulf. In a universe where acceleration weakens, connection lasts longer. Structures endure. The cosmic web remains visible. The universe retains coherence for extended periods. These differences are not philosophical abstractions. They are physical outcomes tied directly to dark energy's behavior. This is why cosmologists take hints of evolution seriously. They are not chasing novelty. They are trying to understand which future is consistent with reality. Importantly, none of these futures unfold on human timescales. Billions and trillions of years separate the present from these endpoints. The universe is not in a hurry, but slowness does not make the question irrelevant. Understanding cosmic fate clarifies cosmic context. It tells you whether the universe tends toward fragmentation or persistence, toward isolation or continuity, toward silence or structure. It also reframes humanity's position. If the universe accelerates relentlessly, the era of visible cosmic structure is temporary. We live in a brief window when galaxies are still accessible to observation. When the universe is still richly populated with information, that window will close. If dark energy behaves differently, that window widens or narrows accordingly. The timing of observers becomes significant. The universe's story includes chapters where understanding is possible and chapters where it is not. This introduces a quiet urgency to cosmology. Not urgency in the sense of crisis, but in the sense of opportunity. There are things about the universe that can only be learned during certain epochs. Dark energy shapes those epochs. The force that drives expansion is therefore not just a physical parameter. It is a curator of cosmic eras. It decides how long stars shine, how long galaxies remain visible, how long complexity persists. That responsibility rests on something we cannot see, touch, or explain fully. This is why changes in dark energy, even hypothetical ones, carry emotional weight. They remind us that the universe is not obligated to preserve conditions favorable to observation or existence. The present richness of the cosmos is not guaranteed, and yet, the universe has already demonstrated remarkable balance. Dark energy did not dominate too early. It allowed matter to clump, stars to form, chemistry to flourish. Only later did it rise to prominence. That timing remains unexplained, whether coincidence or necessity. It underscores how finely the universe's story depends on its ingredients. A small adjustment at the fundamental level rewrites the ending. Cosmology does not claim to predict the future with certainty. It outlines possibilities. It maps trajectories. It identifies sensitivities. Dark energy sits at the center of that effort. If it is constant, the universe drifts quietly toward emptiness. If it evolves, the ending changes. Not suddenly, not theatrically, but inexorably. The force that shapes the universe's expansion also shapes its destiny. And until its nature is understood more deeply, the universe's future remains open, not chaotic, but unresolved. When a result refuses to sit comfortably inside an established model, science does not rush to celebration. It pauses. It asks a harder question. Is reality changing? Or is our understanding failing? Hints of evolving dark energy sit precisely at this crossroads. On one side lies the possibility of new physics, something fundamental missing from our description of the universe. On the other lies a quieter, less glamorous explanation, hidden errors, subtle biases, or incomplete modeling masquerading as novelty. Both paths are plausible. Only one can be correct. This tension defines the current moment in cosmology. The temptation to invoke new physics is strong. History rewards it. Relativity emerged from small discrepancies in Newtonian gravity. Quantum mechanics arose from stubborn anomalies in classical theory. In each case, the universe resisted explanation until deeper rules were uncovered. Dark energy, with its unexplained nature and dominant influence, feels like a prime candidate for such a breakthrough. If dark energy evolves, it suggests dynamics rather than stasis, a field that changes with time, a component of the universe that responds to expansion rather than merely existing within it. Entire classes of theoretical models explore this possibility. Scalar fields that slowly roll, exotic interactions that activate only at low densities, modifications to gravity that emerge at cosmic scales. These ideas are mathematically rich. They offer mechanisms where the cosmological constant offers none. They promise explanation instead of description. But promise is not evidence. Every new physical model must answer to data. It must fit not only the expansion history, but the cosmic microwave background, galaxy clustering, gravitational lensing, and local measurements all at once. A theory that explains one anomaly while breaking 10 established results does not survive. This is where enthusiasm meets discipline. On the other side of the debate lies a more conservative explanation. The hints are artifacts, products of complexity rather than revelation. Cosmological measurements are extraordinarily difficult. They depend on layers of inference. Distances are not measured directly. Expansion is reconstructed indirectly. Galaxy properties evolve. Supernovae may not be perfectly uniform. Dust obscures light. Selection effects skew samples. Each correction introduces assumptions. Each assumption carries uncertainty. A small bias at one stage can ripple through an analysis, producing a trend that looks physical but is not. In large data sets, even tiny systematic errors can become statistically significant. This is not a hypothetical concern. Cosmology has faced it before. Past tensions have vanished when calibration improved. Apparent anomalies have dissolved once new data filled gaps. Results that once hinted at revolution were later understood as artifacts of incomplete modeling. Because of this history, cosmologists default to skepticism. When a hint appears, it is treated as a suspect, not a savior. Analysts ask whether the signal survives alternative modeling choices, whether it appears consistently across independent datasets, whether it strengthens with new observations or weakens. This process is slow by design. Hidden errors are difficult to expose because they often hide in plain sight. A correction applied universally may still be wrong universally. A model may fit current data, but fail subtly at the extremes. To guard against this, modern surveys rely heavily on simulations. Artificial universes are generated with known properties. Analysis pipelines are run blindly on this synthetic data. If the pipeline recovers the correct answer, confidence increases. If it produces spurious trends, the source of error must be found. This approach treats the analysis itself as an experiment. Even with such precautions, ambiguity remains. The most unsettling possibility is that both explanations are partially correct, that the universe contains new physics, but the current hints are distorted by imperfect measurements. In that case, the signal exists, but its shape is unclear. Distinguishing between these scenarios requires more than clever theory. It requires independent confirmation. This is why no single experiment can settle the question of evolving dark energy. Agreement must emerge across methods that share no assumptions. Brightness-based measurements must align with geometry-based ones. Early universe probes must agree with late universe probes. Only coherence across diversity builds trust. This demand for convergence reflects a deeper principle. New physics does not hide selectively. If dark energy truly evolves, its influence should manifest everywhere. Expansion matters, not just in one dataset, not just at one redshift range. Inconsistency points toward error. Consistency points toward reality. At present, the balance is unresolved. Some combinations of data show mild preference for evolution. Others remain fully consistent with a constant. The picture depends on choices, how datasets are combined, which assumptions are prioritized, which uncertainties are emphasized. This dependence is uncomfortable, but honest. It reveals the true state of knowledge, suggestive, but incomplete. The role of theory in this moment is not to declare victory, but to map possibilities, to explore what kinds of physics could produce the observed behavior without violating known constraints, to provide targets for observation rather than conclusions. The role of observation is to narrow those possibilities relentlessly. This interplay is not conflict, it is calibration. Science advances not by choosing sides prematurely, but by forcing both explanations to compete under increasing pressure. Theories must become more predictive. Measurements must become more precise. Assumptions must become more explicit. Over time, one path becomes untenable. Either the hints will fade as errors are corrected, reinforcing the cosmological constant as an effective description of reality, or the hints will sharpen, survive scrutiny, and demand a deeper framework. Both outcomes represent progress. If the hints vanish, cosmology gains confidence in its foundations. If they persist, physics gains a doorway into something new. What matters is not which outcome occurs, but how the decision is made, by patience rather than excitement, by consistency rather than novelty, by doubt applied evenly to data and desire alike. The universe does not reward eagerness, it rewards precision. At this stage, Competing explanations coexist because the evidence allows them to. That coexistence is not a failure of understanding. It is a snapshot of understanding in motion. Science is not a sequence of answers. It is a narrowing of possibilities. And right now, dark energy sits inside that narrowing space, balanced between revolution and refinement, between new physics and hidden error. The resolution will not arrive as an announcement. It will arrive as a convergence. There is a quiet discomfort in realizing that the universe does not promise permanence, not to stars, not to galaxies, not even to ideas. For much of human history, this discomfort could be avoided. The cosmos was distant. Its rules felt eternal. Change belonged to the earth, not to the heavens. Modern cosmology removed that comfort. It revealed a universe with a history, a trajectory, and an uncertain future, more unsettling still. It revealed that our understanding of that universe is provisional, accurate enough to work, incomplete enough to change. To live inside a provisional universe is to accept that knowledge has an expiration date. This does not mean that science is unreliable. It means it is honest. Every model is a temporary truce between observation and explanation. It holds until evidence demands revision. The universe does not wait for certainty. It continues doing what it does while understanding catches up. Dark energy embodies this reality more clearly than any other concept in modern physics. It is not a discovery in the traditional sense. It is a name given to behavior, a placeholder that organizes observations without explaining them. It works extraordinarily well, and that success is precisely what makes it provisional. A permanent answer explains itself. A provisional one works while raising questions. Living inside such a framework changes how you relate to certainty. You stop expecting final explanations. You learn to value constraints over conclusions. You understand that progress often means narrowing ignorance rather than eliminating it. This mindset is not weakness. It is adaptation. The universe has already taught this lesson many times. Newtonian gravity explained motion for centuries, until small inconsistencies accumulated. Classical physics described heat and light, until anomalies forced a deeper theory. In each case, the old framework remained useful even after it was surpassed. Provisional does not mean wrong, it means incomplete. Cosmology today rests on a model that fits an extraordinary range of data. It explains the cosmic microwave background, the distribution of galaxies, the formation of structure, and the accelerating expansion of space. It predicts what we see with remarkable accuracy, and yet, it is built on components we do not fully understand. Dark matter, dark energy, ingredients that dominate the universe but remain invisible. They shape reality without revealing their nature. The fact that they exist at all suggests that what is most important about the universe is not what shines, but what does not. This inversion of expectation forces humility. You live on a planet made of ordinary matter, orbiting a star that represents a tiny fraction of cosmic content. Everything familiar is built from a minority ingredient. The majority governs from the background. That alone should temper certainty. But provisionality goes deeper than composition. It extends to laws and constants. Values, once thought fixed, may be effective descriptions rather than fundamental truths. Relationships that hold today may shift when examined across deeper time. The possibility that dark energy evolves is not alarming because it implies chaos. It is unsettling because it implies contingency. The universe may not be governed by a single, timeless rule, but by dynamics that unfold slowly across epochs. This reframes the role of observers. You are not standing outside the universe, measuring it objectively from a distance. You are embedded within a particular era, one shaped by specific balances that may not last forever. The questions you can ask, and the answers you can find, depend on when you exist. In earlier epochs, the universe was too hot and dense for galaxies to form. In far future epochs, expansion may isolate regions beyond communication. The present sits in between a window where structure exists and information is accessible. That window is not guaranteed. Living inside a provisional universe means recognizing that knowledge itself has seasons. Some truths are available only briefly. Some measurements are possible only under certain conditions. The cosmos is not obligated to remain observable. This realization adds weight to cosmology's patience. The slow accumulation of data is not just a methodological choice. It is a response to opportunity. The universe currently offers access to its large-scale structure, its expansion history, and its early conditions. Those signals fade with time. Understanding is time-sensitive. Provisionality also changes how disagreement is perceived. Competing explanations are not signs of failure. They are signs of engagement. When data does not decisively favor one interpretation, it means the boundary of knowledge has been reached. At that boundary, caution becomes wisdom. Cosmology does not rush to declare revolutions because revolutions cannot be undone easily. They reshape frameworks, reallocate trust, and redefine what counts as evidence. A provisional universe demands provisional claims. This discipline can feel unsatisfying, especially outside the scientific community. Certainty is comforting. Ambiguity feels unfinished. But the universe itself is unfinished. It continues to expand, to cool, to rearrange. Its story is still being written, and any description must remain open to revision. Living with that openness requires a shift in perspective. Instead of asking whether a model is true, cosmologists ask how long it remains useful. Instead of seeking final answers, they seek limits. Instead of defending certainty, they defend process. This approach does not diminish meaning, it enhances it. A provisional universe is not indifferent, it is responsive. It reveals itself gradually, rewarding careful attention and sustained effort. It does not demand belief, it demands observation, and observation, by its nature, is ongoing. For you, living inside such a universe means inhabiting a moment where questions are sharper than answers, where the dominant force shaping cosmic fate remains unnamed in any deep sense, where understanding advances not through revelation, but through refinement. This is not a crisis, it is an invitation to participate in a story that is still unfolding, to accept that knowledge grows not by replacing ignorance with certainty, but by replacing mystery with better questions. The universe does not offer closure, it offers continuity, and within that continuity, provisional understanding is not a flaw to be corrected. It is the condition that makes discovery possible. At the far edge of what can be known, certainty thins out, not abruptly, but gradually, like light fading into night. Cosmology has learned to live in that dimness. It does not mistake the edge for an ending. It treats it as a boundary, one that defines both how much we understand and how much remains beyond reach. Humility begins there. For centuries, the universe appeared stable and accommodating. Its motions could be predicted, its patterns repeated. The heavens felt governed by timeless rules that waited patiently to be discovered. Each breakthrough reinforced the belief that knowledge advanced in a straight line toward completion. Modern cosmology disrupted that expectation. The universe turned out to be larger than imagined, older than expected, and governed by components we cannot see or touch. Dark matter and dark energy do not behave like missing pieces waiting to be slotted into place. They behave like reminders, signals that the framework itself may be provisional. Humility is the only posture that fits this realization. It does not mean abandoning ambition. Cosmology is ambitious by necessity. It seeks to describe the entire universe with a small set of principles. That goal demands confidence, But confidence without humility hardens into assumption, and assumption eventually collides with reality. The history of science is shaped by those collisions. Each time certainty grew too comfortable, the universe introduced a complication. Motion was relative, time was flexible, space curved, expansion accelerated. None of these revelations arrived because science lacked rigor. They arrived because rigor eventually exposed the limits of its own reach. Dark energy sits precisely at such a limit. It dominates the universe, yet resists explanation. It behaves consistently enough to be modeled, but not deeply enough to be understood. It fits into equations without emerging naturally from theory. Its presence is inferred, not experienced. This combination demands restraint. Cosmology does not claim to know what dark energy is. It claims to know what it does. That distinction matters. Behavior can be constrained. Essence may remain hidden. Humility accepts that gap without trying to close it prematurely. This acceptance reshapes how questions are framed. Instead of asking for ultimate causes, cosmologists ask for testable consequences. Instead of demanding final answers, they seek consistency across observations. Instead of certainty, they pursue convergence. These choices are not conservative. They are strategic. The universe is not obliged to reveal itself quickly. It does not reward impatience. It yields understanding incrementally, often through correction rather than confirmation. A humble approach recognizes that pace and adapts to it. There is also humility in scale. Human lives unfold across decades. Civilizations span centuries. Cosmology deals in billions of years. Phenomena that define cosmic fate occur slowly, far beyond any individual timescale. Acceleration, expansion, dilution, these processes cannot be rushed. Understanding them requires a willingness to work without immediate payoff. This temporal humility changes the meaning of progress. Success is no longer measured by dramatic discovery alone, but by improved limits, by reduced uncertainty, by cleaner data, by questions asked more precisely than before. Even null results matter. If dark energy turns out to be constant after all, that outcome will not be disappointing. It will mean that the simplest explanation endured the most rigorous scrutiny. That survival itself would be a form of understanding. Humility recognizes that confirmation can be as valuable as surprise. At the same time, humility keeps space open for the unexpected. It resists the temptation to treat current models as final simply because they work. It remembers that working models can still be incomplete. This balance between trust and doubt is the defining feature of mature science. It is also deeply human. Humility in cosmology mirrors humility in perspective. You exist on a planet orbiting an ordinary star in an unremarkable galaxy. Your species occupies a brief interval in cosmic time, and yet, within that interval, you have learned to reconstruct the universe's history, to measure its expansion, and to infer the existence of forces that shape its destiny. This achievement does not elevate humanity above the universe. It situates humanity within it. Knowing where you stand is not the same as knowing everything. The universe remains indifferent to comprehension. It does not adjust its behavior to match understanding. It simply continues. Humility acknowledges that continuation without demanding resolution. There is also humility in accepting that some questions may remain open indefinitely, not because they are meaningless, but because the universe does not provide the conditions needed to answer them fully. Cosmic variance, observational limits, and the finite speed of light impose boundaries that no technology can erase. These limits are not failures. They are features of reality. Living with them requires intellectual maturity. Cosmology does not promise closure. It promises coherence. It offers narratives that align observation with theory, while remaining open to revision. It teaches that understanding is not possession, but alignment, a temporary harmony between description and evidence. At the edge of cosmic knowledge, humility is not passive. It is active discipline. It governs how claims are made, how results are shared, and how uncertainty is communicated. It protects the field from overreach and preserves trust in its methods. Without humility, science drifts toward myth. With it, science remains anchored to evidence. Even when evidence is incomplete, the story of dark energy is still unfolding. Whether it evolves or remains constant, whether it points to new physics or reinforces existing frameworks, the outcome will arrive through patience, not proclamation. Humility ensures that when that moment comes, whatever it reveals, it will be recognized for what it is, not an ending, but another step. At the edge of cosmic knowledge, humility is not resignation, it is readiness, a willingness to listen carefully to a universe that speaks softly, across distances measured in billions of years, using signals that require extraordinary care to interpret. The universe does not demand certainty from those who study it. It demands attention, and humility is how that attention is sustained.